Hello, AP Physics C students. We're going to look at page 20 of the notebook today on friction. And at the top of the page, we're going to divide this into three sections. The left one, we're going to just review the coefficient of friction a little bit. In the middle, discuss kinetic friction. On the right, we'll deal with static friction. This is just some quick reminders. This is also covered in the types of forces portion of your notebook. And then we have two examples that we'll look at below this for friction on a ramp and a modified Atwood machine. So let's start with the coefficient of friction. Coefficient of friction is the Greek letter mu. M-U. Mu. And the coefficient of friction depends on the two surfaces that are in contact. If you change either of the surfaces in contact, it will change the coefficient of friction. So there is no coefficient of friction, say, for aluminum. It has to be aluminum and what? Aluminum and aluminum, aluminum and wood, or aluminum and tile or granite, marble, aluminum and steel. Any two surfaces, when they slide, they're going to have a new coefficient of friction. If you change either surface, you get a new coefficient. And the coefficient of static friction is going to be greater than the coefficient of terrible. I always have trouble drawing a nice mu. The coefficient of kinetic friction, I'll leave it like that. So static friction is always more than kinetic friction. That's why things kind of leap into motion and static friction breaks into kinetic friction. Next up, we have kinetic friction. Just a few quick reminders about kinetic friction. With kinetic friction, we have surfaces that are sliding. The formula for kinetic friction, the force of kinetic friction, is equal to mu k times the normal force, how hard the surfaces are being pressed together. This only tells you magnitude. It does not tell you direction. I'll put absolute values on just magnitude, not direction. And this type of friction always wants to oppose motion. It always tries to bring the motion to a stop. Then we have static friction. For static friction, the force of static friction, again, this is a magnitude, is going to be less than or equal to mu s times the normal force. Same basic formula as kinetic friction, coefficient times normal force. However, this is the important difference, the less than or equal to. Static friction is not always equal to this. This is the maximum amount of static friction. If this amount is exceeded, it breaks into kinetic friction. But if less than this amount is required to keep the surfaces together, then static friction will be less than that. We'll look at some examples of that coming up. So with static friction, the surfaces stick together. Surfaces stick together. The magnitude and direction will adjust to prevent slipping. And static friction will switch to kinetic friction. If enough force is applied. APP, applied. All right, let's take a look at an example here. We have a block on a ramp. Let's say that our coordinate system here is going to be up the ramp plus perpendicular to the ramp there plus, so that the x direction and the y direction. So one thing that we want to note here is the maximum angle for static friction. And we got a good amount to fit in these next two examples. So be a little conservative with the size of your writing. Now, the maximum angle for static friction means that the force of static friction will be at its maximum. The block is just barely holding on. It is about to slip. And this is going to be equal to the force of gravity down the ramp. The maximum force of static friction is mu Fn. The force of gravity down the ramp is mg sine theta. And that's the coefficient of static friction. Mu s, the force of the ramp on the block, is mg cosine theta. We've gone over those forces previously in the notebook. Now, if I solve for mu, I get mu s is, actually I'm not going to solve for mu, I wanted to find the maximum angle of the ramp. So what I'm going to do is divide both sides by mg. Those will cancel. And I'll divide both sides by cosine theta. That's going to give me mu s equals, and on the right side we have tangent of theta, sine over cosine, tan theta. So I get theta, the maximum angle that the ramp can be at before the blocks slip is the inverse tangent of mu s. So if we know the angle that it slips at, we can find mu s, right? That's using this relationship. So it's easy to find the coefficient of static friction. You put an object on a ramp, you increase the angle of the ramp, you make this ramp steeper and steeper and steeper until the object just begins to slip. The angle at which it's just on the verge of slipping, that angle is the theta max here. And if we take tangent of that angle, we'll get the coefficient of static friction. Let's examine kinetic friction situation here. Oh, actually, before we examine kinetically, let me make one more note about static. If theta is less than theta max, then our static friction is less than mu s Fn. And in this case, what we would have is sigma F equals 0. We'd have the force of friction, which is holding the box up the ramp. That was positive, right? Up the ramp was positive. Minus the force of gravity parallel to the ramp. That would equal 0. So in this case, the force of static friction would be equal to mg sine theta. This is any time the ramp is below the angle at which the block would normally want to flip. Now we'll look at kinetic friction. And for kinetic friction, if we are sliding up the ramp, the force of kinetic friction points down in the same direction as gravity. And if we are sliding down the ramp, the force of kinetic friction points up. This is the force on the block, right? Force of kinetic friction on the block would point in the opposite direction of motion. Let's look at a modified Atwood machine. And again, we got a lot of stuff to fit in here, so be a little conscientious of the size of your writing. We're going to look at the situation with static friction first. With static friction, M1 is at rest. We're going to make 3 comments here. 1, no friction if tension up is equal to mg sine theta. If tension up the ramp is equal to mg sine theta, that means that the force up the ramp is equal to the amount that gravity wants to pull down the ramp. Then the upward force and the downward force are already balanced. We already have sigma F equals 0. We have no net force and no acceleration. If there was friction in this case, it would unbalance the forces that are already there, and it would cause acceleration. And the block would move. But if M1 is at rest and tension is equal to mg sine theta, there is no need for static friction. And in this case, the force of tension here must be equal to m2g. This would be m2g equals m1g sine theta. Next, static friction points down the ramp if tension is greater than m1 g sine theta. That's the force of gravity parallel to the ramp. So what we're saying here is that if this string is pulling up the ramp harder than gravity is pulling down the ramp, right? We would need to balance the forces. If this is not moving, we know the forces are balanced. So if tension's up greater than gravity down, friction must also point down to balance out those forces. Number 3. Static friction points up the ramp if tension is less than m1g sine theta. So now in this case, gravity is pulling down harder than tension is pulling up. So friction has to point up to make the upward forces balance out with the down forces parallel to the ramp. In all of these cases with static friction, we are at rest, so the forces have to be balanced. Then we'll make a few comments about kinetic friction. And we're not going to say too much about kinetic friction here, but need some more space here. The force of kinetic friction is up ramp if the block slides down, and the force of kinetic friction is down the ramp if m1 slides up. And that should make sense, right? The kinetic friction is going to be in the opposite direction of motion. So if m1 is moving up the ramp, friction points down. If m1 is moving down the ramp, then friction is going to point up. There you have it. We'll do the following examples after this in class. You have a good day. We'll see you soon.